Good afternoon. During the last lecture, I proved this lemma, which says that if S is a regular surface and P is a point in it, then the tangent space to the surface at P is spanned by these two vectors, where Q is the inverse image of P by the surface patch sigma. Now I want to make a short remark. Since TPS is a two-dimensional subspace over 3, then we have that TPS passes by the origin of R3. Instead, if we consider its translation to the point P, denoted by P plus TPS, that is the set of vectors of the form P plus V, where V is in TPS. This passes by P and it is tangent to S at P. Now let's see one simple example. It's very easy to check that an open set U over 2 can be regarded as a regular surface. Why this is true? Because we can cover U by the image of a single surface patch given by the identity. So we take sigma from U into U given by this formula, sigma UV equal to UV, where U and V are the coordinates in U. And we get immediately that TPU is R2. Why? Because if we use the previous lemma, we get that TPU is a span of sigma UQ sigma VQ, where Q is sigma inverse P and if you make computation, you will get sigma U Q equal 1 0 and sigma V Q equal 0 1 for any Q. So this becomes span of 1 0 0 1, which is R2. Now we know that if you have a function f defined on an open set U of Rm with values in Rn, smooth, and if V is in Rm and gamma is a regular curve in U with gamma 0 equal P, gamma prime 0 equal V, then we saw that the derivative of f at P applied evaluated at V can be computed as f composed with gamma prime evaluated at 0. Now the question we want to answer is what happens if instead of having a function defined on an open set of Rm, we have a function on a regular surface. So we can give the following definition. Three point two three. So let S be a regular surface and f defined on S with values in Rn, a smooth function. Then the derivative of f at P is the linear transformation df P defined on TPS with values in Rn defined as follows. For all V in TPS, we have that df PV, this is f composed with gamma prime evaluated at 0, where exactly as before, gamma is a regular curve in S with gamma 0 equal P, gamma prime 0 equal V. Now let's explain why DFP is linear and why it is well defined. where well-defined means that this definition does not depend on the curve gamma you have chosen. So if, so let's write y dfp is a linear and well-defined. Okay, let's observe that since f is smooth, then we have that there exists a neighborhood that we will call O of P in R3, not in S. And a smooth function f tilde defined on O with values in Rn, which must be regarded as the extension of the function f, which is initially defined only on S. And this function, of course, of course, agrees with f on the intersection O intersection S. Now we have to use the proposition 3.7, which says that df tilde pv, this is f composite gamma prime evaluated in 0, where gamma, this is f tilde, where gamma is a regular curve in R3 with gamma 0 equal to P and gamma prime 0 equal to V. Now, if we add the additional hypothesis that V is in TPS, then V is the initial velocity vector of a curve in S. By definition of TPS. Let's write gamma. Now, since gamma tilde, since f tilde coincide with f along gamma, I wrote gamma in a strange way, then we can write what do we have here as follows: df tilde PV, which is equal to f tilde composed with gamma prime at 0 as f composed with gamma prime at 0, but this is dfpv according to our definition. So we proved that dfp is the restriction of this map here to TPS. And this map here is a well-defined linear map, and this explains why this one is also linear. And it explains also that this definition does not depend on gamma, because this definition, this formula here says that this expression, which apparently depends on gamma, does not depend on gamma. Another proposition I need to mention is the following. Suppose that f is a function from S1 with values in S2, where S1 and S2 are regular surfaces. Now suppose that this is smooth. Suppose that this function is smooth. Then it is clear that dfp is a map from TPS1 with values in R3, because S2 can be seen as a subset of R3. But since f sends curves on S1 to curves on S2, then if you use this formula, dfp v equal to f composed with gamma prime at 0, you can see, you can regard this as a curve in S2, and then this right hand side is nothing but then the initial velocity of a curve in S2 with initial point f of p. So this means that we can look at this map as a map with values in T f of p S2. And this is what the proposition uh, 3.34 says. Another result we will use in the sequel of this course is the theorem 3.35, is the inverse function theorem for surfaces. We already saw the usual version of the inverse function theorem. It's on page 120. This version here says that if S1 and S2 are regular surfaces, and f is a smooth function from S1 with values S2 in S2, then if for P in S1 you have that the following hypothesis is satisfied. dfp from TPS1 with values in T f of PS2 is invertible, then F restricted to a small neighborhood of P in S1 is a diffeomorphism onto its image, and its image is a neighborhood of f of P in S2. I don't present the proof in detail, I will give you only the idea. The proof uses the inverse function theorem you already know. So let's consider coordinate charts sigma 1 from U1 into V1 and sigma 2 from U2 into V2, where V1 is a neighborhood of P in S1. V2 is a neighborhood of f of P in S2. And up to shrinking these sets precisely U1 and V1, we can assume also that f of V1 is contained in V2. Now let's define the following auxiliary function. Psi from U1 into U2 as follows. Psi equals sigma 2 inverse composed with f composed with sigma 1. This is a map which is defined on U1, so this is a subset of the Euclidean space, and it takes value in another subset of the Euclidean space. Observe also that the differential of this map this is equal to differential of sigma 2 inverse applied at f of P composed with dfp composed with d sigma 1 at Q, where Q is sigma inverse sigma 1 inverse P in U1. The idea is we want to use the inverse function theorem to this function, for this function. Okay, what you have to do is to prove that this map is invertible. So once we will have proved that deep C Q is invertible, apply the usual inverse function theorem to for the smooth function psi. So this says that there exists a small neighborhood of Q and C of Q such that C is a diffeomorphism. Then our goal is not to prove that psi is a diffeomorphism, but if that is that we want is that F is a diffeomorphism, but F is a sigma 2 composed with psi composed with sigma 1 inverse. Since it is the composition of 3 diffeomorphisms, then it is a diffeomorphism. And this is the end of the proof. Actually, it's just the sketch of the proof. Okay, now let's change topic. And let's talk about area distortion and orientation. Okay, suppose that nu and nu tilde are two-dimensional subspaces over 3. And G from nu into nu tilde is a linear isomorphism. We start the study of area distortion by giving the following definition. Definition 3.36, which says that a matrix A equal to AB CD represents G, where G is this map here, with respect to the ordered basis B equal V1 V2 of nu, and B tilde equal to V1 tilde V2 tilde of nu tilde if G of V1 is A V1 tilde plus B V2 tilde, and G V2 is C V1 tilde plus D V2 tilde. Okay, so this means that we are making the following identification. We are identifying nu with the R2 by saying that A V1 plus A V2 is identified to A1 A2, and we are identifying nu tilde with R2, saying that A1 V1 tilde plus A2 V2 tilde is identified with A1 A2. So in other terms, the map G is identified with the linear transformation LA. This is the notation we already used when we studied rigid motions. Precisely, we have the following diagram. So this is a map G, this is a map LA, and these two vertical arrows represent the identification that I presented before. Now we are ready to present the notion of area distortion. So we have the following proposition slash definition 3.37. The area distortion of the map G is denoted by G enclosed by two pairs of vertical bars, and it is given by the length of GV1 cross product GV2 divided by the length of V1 cross product V2 where V1, V2 equal B is a basis of nu, and this definition does not depend on the choice of B. Okay, let's prove it. If you want to prove this statement, you have to consider an alternative basis. So let's choose so proof an alternative basis of nu as the form A V1 plus B V2 C V1 plus D V2. Why? Because this is a basis of nu, and any pair of vectors can be written as a linear combination of V1 and V2. And we need the hypothesis that AD minus BC is non-zero, because we need this to be a basis, and in particular we need these two vectors to be linearly independent and generators. Now, what happens if we compute the area distortion of G using these two vectors instead of V1 and V2? So we have that the area distortion of G is given by the length of GAV1 plus BV2 cross product GCV1 plus DV2 divided by the length of AV1 plus BV2 cross product CV1 plus DV2. Now we want to simplify this formula, and in order to do this you use the properties of the cross product. So precisely, first of all you write G of A V1 plus B V2 as A GV1 plus B GV2. You do the same with GCV1 plus DV2. And you use the fact that GV1 times GV2 is equal to minus GV2 cross GV1, and GV1 times GV1 is 0, and so is GV2 cross product GV2. You will see that the numerator becomes AD minus BC times the cross product of GV1 and GV2, What about the denominator? You use the fact that V1 cross product V2 is minus V2 cross product V1. V1 cross product V1, this is 0, and this is also V2 cross product V2. And you will get that the denominator is AD minus BC multiplied by V1 cross product V2. Then you simplify, because this is the absolute value of AD minus BC times the length of this vector, and the denominator is the absolute value of this number times the length of this vector here. So you will get the length of GV1 cross GV2 divided by the length of V1 cross V2. So what we got? We got that this is equal to the distortion of G computed with the definition I gave you before. Okay, what is interesting is that the area distortion is also equal to the absolute value of the determinant of the matrix which represents G. This is the content of proposition 3.38. Let's prove it. So suppose that B equal V1 V2 and B tilde V1 tilde V2 tilde are the basis of nu tilde. If the matrix which represents G is this one, then GV1 is A V1 tilde plus B V2 tilde, and GV2 is C V1 tilde plus D V2 tilde. Then we can compute the distortion of area of G by using the formula I gave you before. If you replace GV1 by this vector, GV2 by this vector, Using one more time the algebraic properties of the cross product, you will find AD minus BC times V1 cross V2, sorry, V1 tilde cross V2 tilde, divided by V1 cross V2. Sorry, I omitted one important detail in the statement. The basis that you use for nu and nu tilde must be orthonormal. Okay, what happens if the bases are orthonormal? It happens that the length of this vector and the length of this vector will be 1. So as a result, the area distortion of G is the absolute value of AD minus BC, and this is the absolute value of determinant of A. So remember, in this proposition you need the orthonormality of the basis, otherwise you cannot prove it. Okay, let's see one simple example. Consider the map DFT represented by this matrix cosinus of theta minus r sinus of theta, sinus of theta, r cosinus of theta. To get this matrix, if you compute the derivative of the map f r theta equal r cosinus of theta, r sinus of theta, which encodes the change of variables. You change the variable from the Cartesian one to the polar one. So a simple computation shows that the area distortion of this map is equal to R where I am using this notation for the matrix you have here, and this is R. Okay, so what we proved so far is the following. The area distortion is basis independent if the bases we use are orthonormal, why this is true? Because we proved that area distortion is equal to determinant of A, and the determinant of a matrix which represents a linear transformation does not depend on the choice of the basis. So the area distortion is a basis independent. Now the next remark I want to make is about the sign of the determinant we would like to make it basis independent. It is possible to do this, and it is necessary to introduce the definition of positively oriented basis. Why? Because if, for example, I work with this pair of bases and I compute the determinant of A, then I make one change, which change I, for example, work with B tilde given by V2 tilde, V1 tilde. Then the sign changes. The sign of determinant of A changes. So this means that we need to work with spatial ordered bases, where the order matters. So we give the following definition: 3.40, which says that an orientation for nu means a choice of a unit length normal vector denoted by n to nu with respect to this orientation an ordered basis V1, V2 of nu is said to be positively oriented if V1 cross product V2 divided by its length is equal to n. If instead you have the other sign, I mean V1 cross product V2 divided by its length is the opposite of n, it is called negatively oriented. So this definition says that there are exactly two orientations for nu. Another tool we will use in the sequel is the following, is the counter clockwise rotation by 90 degrees. So once you have fixed an orientation on nu, then we can define a counterclockwise rotation. Sorry, I think that before I said counterclockwise orientation, I meant counterclockwise rotation. Sorry for that. How to define a counterclockwise rotation? This can be done as we did in R2. So we have a map R90, but this time it is defined on nu, it takes values in nu. Now, the problem of this definition is that apparently it is dependent on the basis. But in a moment, I will show you that if you have an orientation on nu, this definition is basis independent. So the dependence on the basis is only apparent. Why? Because you can prove very easily that R90 of a vector v in nu can be written as n cross product n cross product v, where n is the orientation we chose for nu. How to prove it? Suppose that V1, V2 is an orthonormal basis of nu. Then you can choose, for example, n to be V1 cross product V2. Then if V is equal to a V1 plus B V2, what is n cross product V? This is V1 cross product V2 cross product A V1 cross product, plus B V2. That is a V1 cross product V2 cross product V1 plus B V1 cross product V2 cross product V2. Sorry, I made a typo. I don't need to write, I don't need to expand, I don't need to expand n, sorry. Let's write just n here, and we get a n cross product V1 plus B n cross product V2. If n is V1 cross product V2, then using the right hand rule, you find that if the basis V1 and V2 is the one I sketched on the blackboard, then n points this way. Then what is n cross V1 is a vector of length 1, and it points like V2, so it coincides with V2. Instead, what about n cross product V2? Using the right hand rule, you get that it points like minus V1, and you get minus B V1 plus A V2. This is exactly the formula I gave you before. So this definition is basis independent. The last definition I want to give you is the definition of orientation preserving map. The map G is said to be orientation preserving with respect to given orientations of nu and nu tilde if one of the following equivalent conditions are satisfied. One, if B equal V1, V2 is a positively oriented basis, ordered basis of nu, then GV1, GV2 is a positively oriented basis of nu tilde. What is the condition number 2? The matrix which represents G with respect to any positively oriented ordered basis for nu and nu tilde has positive determinant